All right, so here we go. This is the final from fall 2021. I hope you guys did well. Here we go. Here's the key. Okay, so the first thing we're going to do is we're going to do a shear and bending moment diagram and label all important values on the graphs. Okay, determine magnitude, location, and maximum absolute value of shear and bending moment. Okay, so let's see here. So the first thing we're going to do before we even, begin to tackle this problem is I'm going to draw my forces, A, Y, and B. B is a roller, right? So we don't even have an AX. We don't even have a BY. BX. But the AX is 0, so I'm not even going to bother drawing it because there's no forces in the X direction. So in the Y direction, this is going to be AY, and this is just going to be B. And I'm just going to leave them like that. I'm not even bother drawing to AY. Okay, so let's go ahead and let's imagine, so this force right here, this 40 kilonewtons per meter, we're going to, at least for now, imagine it as, 40 kilonewtons per meter over 8 meters. So we're going to imagine it as 320 kilonewtons acting 4 meters from A. So that's going to be 4 meters right there. And we'll work with that to solve for our reactions. Okay, so I'm not even going to bother doing the sum of forces in the X. Sum of forces in the Y, I could do that, but that's not going to be solvable at the moment because we've got 2 forces. So 2 unknowns is not really going to be work for me. However, if I do the sum of the moments, if I do that either A or B, this will solve out. Okay, so I'm going to do it at A. Obviously, I could do it anywhere I wanted to, but it seems silly to not do it at a place where that's going to be a little bit easier. So let's see here. So we're going to start with that 320 kilonewton force, 320 kilonewton force. Okay, and that's acting 4 meters from A. The nice thing about these are all perpendicular distances, so I don't even have to really worry about that too much. And that's going to cause things to go clockwise. It's going to get a negative. Okay, and then I've got B is the next one up. B is going the opposite direction. Okay, it's going to cause a counterclockwise rotation, and that one's 8 meters away. And then I've got that 20 kilonewtons, so that's going to also cause a clockwise rotation, so 20 kilonewtons. And its distance is 11 meters, which is kind of an annoying number, especially when everything else is divisible by 4. But lucky for you, I spent a little time last night figuring out what that moment should be, and I made it so there's an extra moment right there, that 140 that's being applied, that 140 kilonewtons times meters equals 0. Okay, and so I intentionally, spent a little time last night trying to figure out what that moment should be so it would give you a nice clean number. So B comes out to, not as clean as we would like, but 205 isn't so bad, if you do the algebra there. It could have been worse. I think when I first did the problem, it was like 202.375 or something. And I was like, I don't want y'all to have to deal with that. So if you really stare, you can see I doctored that 4. I had to copy this 4 and squeeze it over there. Anyway, okay. Anyway, so then we'll do the sum of the forces in the vertical. Sum of the forces in the Y equals 0. Okay, and I've got, let's see here, I've got AY is going up. Looks like I'm kind of leaving myself some space here. So I've got AY going up. I've got that 320 coming down. I've got B going up, and I've got 20 going down. Okay, so if I plug in B from up here, I've got AY minus 320 kilonewtons plus 205 kilonewtons minus 20 kilonewtons equals 0. So AY equals, 340 minus 205 is 135, I believe. So 135 kilonewtons. Okay, so there we go. Okay, so let's come back over to our, force here. I'm going to go ahead and erase this because we're no longer going to use that for our way down. And I'm going to erase these letters too because we don't care what we called them. Okay, because that's not really all that important. Okay, so B is 200, come on, baby. 205 kilonewtons, and this one's going to be 135 once it decides to allow me to erase it. Okay, there you go. So it'll be 100, come on, you can do it. 100, come on. 135 kilonewtons. Okay, so there we go. So now we're pretty much ready to go. We're going to bring out our trusty ruler. Now I apologize, or maybe maybe you like it. I don't know. I watched some of my old videos, and I could hear the sound of me slapping this ruler around. And it, you know, for me personally, I kind of like this sound of that ruler coming down, but maybe you don't. In which case, I apologize. So now we've got these. These are our points of interest. I think there ends up being one more point of interest, but for now, those are our points of interest. So I'm going to start right here. I'm going to do, you know, this is going to be my V diagram, V, and I'm going to go ahead and put the kilonewtons over here because I don't want to have to draw them on the diagram. All right, so now we're going to, I guess I'll do this in kind of red, so it'll be kind of in contrast to the blue that's above it. And so we're going to go up 135, so I'm going to start at 0. There's no shear at the edge. So I'm going to go up 135. Let's see, how should we do that? Let's do, each block is 25, so this is going to be 125 and 135 is going to be about right there. Okay. Now we're going to go down 40 kilonewtons per meter over 8 meters. So we're going to go down a total of 320 kilonewtons per meter. So I started at 135 right here. I'm going to go down 320. So I'm going to end up at negative 185, right? So if I do my boxes here, let's see, 1, 2, 3, 4, that's 100, 175, and here's maybe 185 right here. Okay, so I started at 135 and went down 320, because that's 40 kilometers per meter over 8, right? So here we go. Okay. So that's going to put us down at negative 185, okay? At which point we're going to go up 205. So I'm going to go from 185 up to, let's see, negative 185 plus 205. We're going to go to positive 20. So we're going to go up to about right there, more or less. Okay, so that's a 20. And then nothing happens between B and C. So the shear is just going to remain constant. Okay, until I get here. And then I've got that 20 kilonewtons to drop me right back down to the bottom. Okay, so that's that. The next thing that I need to know is I need to know this position right here. Okay, on my key I called it X1. Just, I don't know why I called it 1. Oh, because there's going to be another X coming up. And so what I would do, I mean, there's a few ways you can do it. I just think I'm at 135 and I'm going down 40 kilonewtons per meter. So if you do 135 divided by 40. Another way you can do it is we can solve for the equation of this line right here. Which is pretty straightforward, right? So it's y equals mx plus b, so v of x equals m. M in this case is negative 40 kilonewtons per meter, okay, times x plus, you know, well, what is v when x is 0? It is 135. Okay, so y equals mx plus b. Okay, so we go ahead and solve that. So if we solve for, you know, when is the shear 0? Shear is 0 at what I'm going to call x1, negative 40 kilonewtons per meter, times x1 plus 135 kilonewtons. So if you solve that, you're going to get x1 is equal to 3.375 meters. Okay, so this is going to be 3.375 meters. Okay. Now the other thing that I like to do, that's just, I mean, I don't know, there's a lot of different ways to do this. Let's go ahead and get the areas of these triangles. Okay, so the area of this triangle is the base times the height divided by 2. And we're going to get 227.8125. And there's units on that, kilonewtons per meter, or times meter. Okay, and then for this triangle, the area is going to give me a negative value. And of course, this distance is going to be, this distance right here, is going to be 8 minus 3.375. So that's going to be what, 4.525, I think? That looks right, 4.525. Sorry, 4.625. Okay, so we'll take the base of this triangle times the height, and we'll divide by 2. And we're going to get a negative 427.8125. Okay, kilonewtons times meters. Okay. And then we'll get the area of this one right here, which I'm just going to kind of write over here, and it's going to be a positive. We'll look, let's see, it's space times height. So it's 3 meters times the height of that thing, which is 20. So it's going to be 60 kilonewtons times meters. Okay, so armed with this lovely knowledge, let's go ahead and, I don't know why. It's very typical to shade these things in. I don't know where this comes from exactly. But you see everybody likes to shade them. Okay, whatever. So anyway, so we're going to go down here, and we're going to go ahead and, we're going to plot our moment diagram. And I, of course, have not left myself a ton of space, but I think it will be okay. Okay, so this is moments in kilonewtons times meters. Okay, and we'll do this in red. Okay, and so the first thing the first thing I need to be aware of is that there is an extra point of interest right here, right there. Okay, and then so let's go ahead and we're going to start at 0. Well, hold on. Are we starting at 0? Yes. Look, there's no moment right here. There is a moment right here. So we're not necessarily going to end up at 0 on the far end, and then we're going to jump 140 kilonewtons per meter to get back to 0. Okay, so anyway, so we're going to start at 0. Okay, and we're going to start with a slope of 135. So that means we're going to start going upwards. Okay, when we get to this vertical dotted line, I'm going to have a slope of 0. Okay, so somewhere up here it's going to be like that. Okay, where? Well, the area tells me. Okay, so 227 point, whatever. So if I do these blocks and I say, let's see, every block is, I don't know, 50 kilonewton meters. So we're going to go up 1, 2, 3. That's going to be 200. And then we're going to go up, about half of another one of those. Okay, so let's ignore this little line that I put there. And let's just, we're going to kind of do like this. Oh, that's not very good. Okay, so it's going to flatten here. There you go. Okay, notice these are my large values on this graph, so they're the large slopes on this graph. Okay, these are my small values, so they're my small slopes over here. Okay, the value right here is 227.8125. Okay, it is basically the cumulative area up until that point. Okay. Okay, now we're going to go down. So now I'm going to add this area, 427.825, or we're going to subtract 427.8125 from that value, 227. Okay, so if we start at 227 and we use this as our change, okay, we're going to go down to negative 200. So it looks like that's about as low as my plot got, using, each box is it's 50 kilonewton meters. So we're going to go like this. Okay, now how did I know it was continuing to get steeper? Well, the slope right here is negative 185, so it's going to be really steep. The slope right over here is 0 because that's the value up there. Okay, so now we've got, so I can continue to shade this in if I wanted to, right? Okay, as you guys turned it in, I noticed one of you solved for this as a location of interest right here. So I'm going to call that x2, and we'll do that in a second. But I didn't ask for that. Okay. So anyway, so 227.8125 minus 427.825 gets me down to negative 200. Okay. Now what I'm going to do is I'm going to add this 60 right here. So I'm going to get to 140. So what's 140 is about? It's about right here maybe. Okay, and we'll notice that the slope along there is the same everywhere. It's a positive number and it's constant. It's not changing. How do I know that? Because the value here tells me the slope right here. The value here tells me the slope right here, et cetera, et cetera, et cetera. And those values aren't changing, so the slope isn't changing. Okay, so this will go. Okay, and this is negative 140. Okay, so then we're going to go back over here and we're going to look at this 140. Okay, and that looks good. So we're going to just shoot right on back up. Okay, so the last bit we might want to know is we might want to know where this x2 is. So to get x2, notice that's in the same section that I did this earlier, right? So right up here, this is from section 1 when I defined the shear, right? So if this is still section 1 that I'm looking for x2 in, I can kind of continue with that line of thinking, and I can I can just do I can integrate that equation, right? So I'm going to say, so instead of negative 40 kilonewtons per meter times x, well, now I've got an x squared over 2, right? Because I'm integrating, so it's going to be negative 20 kilonewtons per meter, because I had the x squared over 2 in this case. And then I can add the 135 kilonewtons times x. And then I can add, my b, right? Or and this, you might think of it as your c. I think of it as an m naught, okay? So if I plug in x equals 0, what moment do I get? Well, if I plug in x equals 0 here and here, both of those terms go away. And the moment that I get from right over here is 0. So that means m naught has to be 0 in order to satisfy that equation. So we're just going to kind of get rid of that. Okay, that won't always work out nice and pretty like that, but it did in this case. Okay, so if that's the case, then I want to know, let's see. So I want to know x2 is when the moment is 0, right? x2 is when the moment is 0. Okay, so let's go ahead and solve this. So 0 equals negative 20 kilonewtons per meter. Okay, times, I call this x2 squared plus 135 kilonewtons times x2. Okay, so this is a quadratic, so therefore you're gonna have two solutions. And so what we'll do is we'll say, okay, let's go 0 equals, and I've got x2 factored out of negative 20 kilonewtons per meter times x2 plus 135 kilonewtons. Right, so there's our, that's kind of our two solutions, right? So you remember in high school you kind of split this in half. Usually you draw a little line like this. So one of them is x2 equals 0, and the other one is x2, well, I guess it's not as straightforward as that, right? It's 0 equals negative 20 kilonewtons per meter times x2 plus 135 kilonewtons, right? So we can solve this one, and we get x2 equals 6.75. 6.777, you punk, 75 meters. Okay? And booyah, right? So now I can say that x2, well, x2, let's not do it like that, equals 0 and 6.75 meters. Okay, so we've got an x2 right here, and we've got an x2 right here. So this x2 equals 0, and this x2 equals 6.75 meters. Okay, probably if you did that, I'll probably just give you some bonus points or something. I wasn't expecting that. Should have been able to do it. We did go over how to do that, but it's okay. Okay, let's see. All right, so that's problem 1. Oh, here we go. The maximum shear. Okay, and in this case, I mean the absolute shear. So maximum shear is 185 kilonewtons. And that is happening, what, 8 meters from A? Oh, okay, 8 meters from A. And the maximum moment is, looks like it's 228 kilonewtons. And it's located 3.38 meters from A. Okay, cool. All right, let's go on to the next one. Determine the location of the centroid of the region shown below. Okay, so the first thing we need to figure out in these is if we want to do vertical or horizontal boxes. I did not do the horizontal boxes. I didn't even do them on my key. If you did, I'll have to figure that out. But here I'll show you why in a second. And the second, it is because of this. All right, so here's our horizontal box. Okay, the problem is that this is x comma y. But, x comma y is defined right here, right? So this thing might have a height of dy, but it's got a length of like a minus x, right? I don't want to deal with a minus x if I can avoid it. It might actually end up being easier, I don't know, but I didn't do it that way. So I'm pretty sure that the vertical boxes are going to be easier, so that's the way that I went. I'm sure I'll have to solve this both ways, because some of you are going to go both ways. But for this key right now, and maybe I'll end up doing it both ways. But right now I'm going to do the proverbial vertical box. Okay, don't be scared by proverbs. Okay. Okay. So the width of that thing is dx. Well, okay, let's not get ahead of ourselves. This location is x comma y. Okay. This thing has a width of dx. Okay, and it has a height of y. Okay, now let's find the centroid. The centroid's like right here. Okay, and it's got a location. You know, it's got, so if this is x right here, okay, then this is also x. So its location is x. Okay, and if this is y, right, then this right here is y on 2. Y on 2. Boom. Okay. So we can go ahead and start working this sucker. So let's see here. So x bar, the old x bar equals, okay, the integral. We're not going to put the limits on there just yet because it's just going to make my work sloppy. Not that we can't. So it's x tilde dA on the integral of x, of just dA. Okay, so the weighted, so just dA. Okay, so the x tilde, in this case, if we look at our thing right here, well, that's just an x. So let's just go ahead and let's zoom in a little bit, right? So we're going to get a x. Okay, and then the dA. Well, that's just the area of that blue thing, right? Okay, so it's dx wide by a height of y. Okay, so y dx. Okay, y dx integral. Okay, and then over here, it's just that same dA. So it's the height of it is y, and the width is dx. Okay. Now, of course, the problem here is that we cannot work. We've got dx, but we've got a y in there. So what we want to do is we want to take this thing right here, and I want to rewrite it so that I have y as a function of x. So if we do the algebra on that, and I'm not gonna spend a lot of time on doing that, but it's what, x on k equals y, and then I take the third root of both sides. So it looks like that, right? Which is, you know, ugly. Anyway, so that's what we got. Okay, so we will use this wherever we have y. Okay, so let's go over here and let's see here. So I'm going to get zoom on in. Okay, so x bar equals. So in place of these y's, I'm going to put x to the 1/3 over k to the 1/3. Okay, and luckily that's not too painful in the case of x anyway. So we've got x, and then y is going to be x to the 1/3 over k to the 1/3 times dx. Okay, and over here we're going to do the integral of x to the 1/3 over k to the 1/3 dx. Okay, all right. I guess there's nothing to do but to just start working it, right? So integral. I've got 1 over k to the 1/3. K is a constant, so I can just pull it right out. Okay, which of course means, you know, lucky for us, those are just going to cancel right out, so we never have to write them again. Okay, and then we've got x to the 4/3 dx, x to the 1/3 dx. Okay, so at this point, it's probably good to put in my, my limits of integration. So I'm starting here. Okay, that's where the first box is, and I'm going to the last box at A. Okay, so this is going to be from 0 to A, 0 to A. Okay, so let's see here. So we'll do x bar equals x to the 7 over 3. Okay, 3/7 over. Okay, and that's going from A to 0. And on the bottom, I've got x to the 4/3, 3/4, A to 0. Okay, so I think if we did the math on that, we're going to get, all the A, well, let's see. The top one becomes A to the 7/3, the bottom one becomes A to the 4/3 if we ignore the coefficients. So that just becomes an A. And then the 3's cancel. So these 3's are going to cancel. And I'm going to put the 4 over 7. So with this, if you plug it all in, you're going to get 4/7 A. Okay, so that's pretty nice. This one you didn't even have to really worry about the k. It just kind of goes away on its own. Okay. All right, so that's one of them. Okay, let's do the y bar, shall we? Okay, let's see here. Here's a y bar. Okay, the integral of y tilde dA over the integral of dA equals, okay, the integral. Okay, so on the bottom, okay, so the dA. Let's talk dA again, just to make sure that you're following here. Okay, the height of this box, okay, is the same as this coordinate. Okay, so it's a y. Okay, the width of that box is just a dx, right? So it's a small incremental x. Okay, dx. Okay, so up top we're going to have a y dx, right? But now I need to know what is the location of the y centroid. Right, so we're going to go right here, and look, there it is right there, y over 2. Okay, y over 2. Okay, so not as, well, it's a little bit less ugly than what we had earlier. But again, you know, we've got dx's and we've got y's, so we can't solve that. But let's go ahead and simplify before we do that. So I'm going to get 1 over 2, because I'm going to pull that 1/2 out, because I don't like that. Okay, y squared dx on the integral of y dx. Okay, so that's cool, but we need this equation right over here, because I want to turn y's into x's. So x to the 1/3 over k to the 1/3, which is totally annoying, equals 1/2. One day I'm just going to give people a triangle. Is the integral of, so instead of y to the 1/2, I'm going to have x to the 1/3 over y to the 1/3 squared dx over the integral of x to the 1/3 y to the 1/3, oh, k to the 1/3, sorry. That's, you know, my apologies. K to the 1/3, that's what happens when you're, you know, not looking at your work while you do this. Okay, so there you go. Let's see what's going to happen there. Well, I think we're going to want to pull those k's out. So we're going to take this squared and we're going to distribute it, and then we're going to take the k's out, or, you know, whatever. So I'm going to get 1 over 2. And on top I'm going to get 1 over k to the 2/3 over 1 over k to the 1/3, because I'm pulling those out of those integrals. And then I have an integral of x to the 2/3 divided, dx, divided by the integral of x to the 1/3 dx. So all of a sudden, you know, and again, we're going from a to 0. So all of a sudden, those integrals aren't so bad. It's all these stupid k's, right? The k is kind of our problem here. Maybe not our problem, but it's an issue, right? So if you do your exponent rules, you know, and you just kind of keep you know, working away at that, you're going to get 1 over 2 k to the 1/3, okay, which is totally annoying, right? But then we got to do this. Then we have to integrate these things. So this goes to x to the 5/3. So this is a 3/5. Okay, and that's going to go from a to 0. That's on the top. I'll put that in parentheses. And on the bottom, we're going to go x to the 4/3 to the 3/4 from a to 0. All right. Okay, and then we'll go equals 1 over 2 k to the 1/3. And then what this is going to be, 4/5, I think? Yeah, 4/5. 4/5. Because those 3 cancels and the 4 goes up and the 5 comes down. And then we've got a to the 5/3 over a to the 4/3, which I believe is a to the 1/3 if you just subtract. Yeah, so this is a to the 1/3. Okay, now we've got an annoying thing. Sorry, I'm losing track of my y bar. Okay, now we've got an annoying thing that I wanted this as a function of a and b only. It's really ultimately, so if you got here and you didn't get the last bit, that's okay. But I mean, I'll still take off, but I'm not going to take off a ton. After all, this is a 20-point problem. But k to the 1/3, we got to deal with that. So I've got 1 over 2 something to the 1/3, 4/5. Oh, I guess I could have combined those two in that 4, right? A to the 1/3. So what is k in terms of a and b? Okay, so here's our equation right here. Okay, and I'm going to bring it over here. I'm going to say x equals ky cubed. And I need a point off of there, right? So one point I could choose is right here. I only know 2 points, 0, 0. But that point's completely unhelpful. So I'm going to choose this point right here, which is a comma b. Okay, and for x, I'm going to plug in a. And for y, I'm going to plug in b cubed. Okay, and that allows me to say that k equals a over b cubed. Okay? Which turns out that that's actually going to be really nice for us. A over b cubed. Okay, and hopefully you can already see why. Because now I've got an a to the 1/3 on top on top of this thing, and I've got a to the 1/3 on the bottom. So those two things are going to cancel. And then I've got this b cubed to the 1/3, so this is going to come b to the 1, right? And it's because it's on the bottom, it's going to be brought to, because it's the denominator of something that's in the denominator, it's going to go to the numerator. So we end up with, I'll let you do the algebra there. You guys know how to do algebra. Let's see, so this 2 and this 4 becomes a 2. So we end up with 2/5 of b, which is a very satisfying solution. To me, at least. I hope you enjoy it too. Okay, so I think whoa, don't turn that now. Okay, so I think, there's our answer. So 4/7 of A and 2/5 B. So 4/7 A and 2/5 B. Okay, let's see here. Number 3. Oh, yeah. I was kind of trying to avoid doing this one. These are just, so much busy work. Give me a second. All right, so if we're going to work this problem, we're going to break this sucker up into some shapes. I'm going to kind of zoom in on it, obviously, if you can, It's always good to do that, right? So here's shape 1, shape 2. I'm just kind of following my key here obviously you can do whatever shape you want. This will be shape 3, and the circle will be shape 4. So what we're going to do at this point is we're going to start trying to identify, where the centroids of each of these things are. And I'm going to go ahead and draw some dividing lines so that hopefully that will make things a little bit easier to see, as far as what is what. And then I'm going to use this same red color. Maybe I'll use blue. Okay, so the centroids of these things, so like this one, so for number 1, it's about right here. And it's 1/3 in this direction, and it's 1/3 in that direction, right? 1/3 of those bases, okay? So if you look that up on the chart, it's going to say 1/3, this one right here is 1/3 of this line, right? So that line being 110, so this distance is 110 over 3, okay? This one right here is 1/3 of this line. That line being 50, this is 50 over 3, okay? So now that's cool and everything, but we need this in terms of, where it is relative to the kind of the global 0, 0. So here's the global 0, 0 right here. And so in x, we're going to go this way, 50, and then we're going to come back 50 over 3. So that's going to be 100 over 3. All right. And then in the y, well, in the y, we're just going to go up 100 over 3. 110 over 3. And I'm forgetting here, of course, I'm getting a little bit ahead of myself. We only care about y bar. So we don't even really need to worry about x bar. So this 100 over 3, it's cool and everything, but we don't, it's right, but, we don't need to know it. I'll go ahead and do the x bars for all of these just because it's not really a bad habit to get into. So this one right here, okay, this one's about right here. And remember, it's going to be 1/3 of the way up here. So that's 1/3 of this side. That side looks like it's 110 minus 45, so that's what, 65. So this distance is going to be 65 over 3 in the y direction. And then this distance, okay, it's going to be 1/3 of this side. So that's 100 minus 50, so that's 50 over 3. 50 over 3. I shouldn't put a comma there, right? Because, that's relative to some like imaginary point right here. Well, we don't really care about that. We care about its point relative to 0, 0, right? So to get there, let's see, in the x direction, I need to go 50, and then I need to get an additional 65 over 3. So that's what, 215 over 3? This is 215 over 3. And in the y direction, I'm going to go up 45, and then I'm going to add 50 over 3. So 45 times 3 is 135. 185 over 3, I think that's right. 185 over 3. Yeah, that's it. In fact, there's an error on my key about that, so I'll have to fix that one. Anyway, and then we're going to go to this third one, okay? And its local equilibrium is about, like, you know, relative to this point, I guess, is basically half and half, right? So in the x direction, it's half of this, which is going to be 50. Sorry. Sorry, it's half of 50. So it's going to be 25. Again, we don't really care about that. And in the y direction, it's going to be half of 45, so it's going to be 22.5, okay? However, we don't care about that. We care about more of, like, it's global. So in the x direction, we've got 50 plus 25 is 75. And in the y direction, we've just got 22.5, okay? Oh, and the centroid of the circle is the easiest one of all because, you know, locally, it's just 0, 0. So, you know, because it's obviously the center of that circle. Globally, it's 50 to the right, and it's up 45, okay? So that's basically a mess, right? But we're going to go ahead and we're going to organize all that data down here. And we're going to go the y tilde, and we're going to go the areas, okay? So the y tildes, we're not going to worry about those x tildes. So here's shape 1, 2, 3, 4. Okay, so shape 1, y tilde is 110 over 3. Maybe we should put that in, let's go ahead and put that in decimal form. You know, you guys know how I am about sig figs. Okay, this has units of millimeters. This has units of millimeters squared. Okay, so then for number 2, we're up here at 185 over 3. So if we divide that, wait, hold on, there's an error here, right? 45 plus 65 over 3. So 45 is 135 plus, what was this? This was 65 over 3. 65, 135 over 3, that's this. This is 65 over 3. All right, so this should be, sorry, this should be 200 over 3. I apologize. 200, dadgummit. Has frozen again. 200 on 3. Okay, so if we divide that, we're going to get 66.667. Okay, so let's go to shape 3. That's this rectangle. The rectangle is 22.5. And then number 4, it's 45. Okay, so now we need to get the areas of all these. These are, I mean, you know, the areas of these are much more trivial than other things we might get. So the area of this first triangle, let's see, you know, it looks like we're 50 along the bottom. We multiply it by 110 going this way, and then we divide by 2, and we get 2750. 2750. Okay, and then the second triangle, let's see, we've got 50 along the bottom. We've got 65 going this way. So 50 times 65 divided by 2, 1625. Area 3, we got 50 times 45, so that's, what is that, 2250, I believe, 2250, yes, 2250. And then we've got this circle right here, which is going to be pi times the diameter squared divided by 4, or pi r, r squared. And if you plug that in, you'll get negative 490.87, where we remember that that is a negative sign because it's, you know, because it's a cutout, you know, so this has been removed from the shape. Okay, so now at this point, we're just going to multiply column 1 times column 2. So I'm just going to go ahead and fill this in. Okay, so it looks something like that. And then what we do if we want to find the y bar is we're going to take this one, and we're going to add, we're going to sum each of those two. So this one's 23, 7, and I got even more sig figs than I need here. And it looks like I did the same thing here, 613, 6, whatever. That number, okay? And it doesn't really matter. As long as you have at least 5, I'm happy. So y bar equals, the the sum of the y hat A over the sum of the areas. And so that's going to be 23,704 millimeters cubed divided by 6,134.13 millimeters squared. So y bar equals 38, I'm just going to keep 5 sig figs here, 751 millimeters. Okay, now obviously, we're not going to report that. So like down here, we're going to put 38.8 millimeters, 38.8 millimeters. Please don't forget your units. Okay, so now we've kind of got some issues here because this is a giant mess. So I'm going to get rid of my mess here real quick. Give me 1 second. All right, so now we want to figure out, we need a global equilibrium here. So global equilibrium, the global, we're looking for the difficulty of bending this thing around the centroidal axis. So we figured out that the centroidal axis is that y bar equals 38.7, whatever. So it's somewhere, let's put it like, I don't know, let's put it like right here. Okay, so that's y bar equals 38.751. Okay, this is units of millimeters. Okay, obviously that's not exactly perfect, but we need to start going with these distances. So we need these distances to that line in order to deal with our parallel axis theorem here. Okay, I gave these locations their y coordinate, but not their x coordinate, right? So because I didn't want to muddy up the works. Oh, whoops, this one needs to go all the way down to here, doesn't it? Okay, so now that we've got all of those, what we're going to do, okay, so we need to figure out what those distances are. And I just created a column for distances in millimeters. Okay, and that's the distance between the local centroid and the global centroid. And so basically, I'm looking for this compared to this. Okay, so I'm just going to subtract them. And what I'm going to do is I'm not going to bother with the absolute value, right? Because we're going to square all these things. So 2.084. I'll subtract this one from the global. And I'm going to get 27.916. And then I'm going to do this one to the global. And I'll get 16.251. And then I'll do this one to the global. Okay, and that's going to be 6.249. Okay, and there really isn't a reason to have this line underneath, right? Because we're not going to sum that. Okay, so the next column is AD squared. Okay, so I could get that. I'm doing that parallel axis theorem. Now note, I did that before I did IX. You could have done IX first. I just kind of liked having, I don't know why I did it in that order, but I did. Okay, so we're going to take this area, and we're going to multiply it times this squared. Okay, and assuming I don't have any errors here, 943. So we can go A times this one squared. And that's the big one, 1,266,367, right? Way too many sig figs. And we'll do this one times this one, and we'll get 594,214, and then we'll do it one last time. And we're going to end up with a negative here, so just be careful and remember that. In fact, now that I remember that, I'm going to go ahead and put my negative here too, because I don't want to miss that. Okay, so this is going to be 19,168. Okay, so pretty small. Ultimately, that circle is not terribly important. We'll go ahead and sum all those while we're here. So it'll be 1,853, 356. Okay, and then for the IXs, okay, well, the IXs are going to require, they're going to require just using formulas, right, out of your equation sheet. And for a triangle, okay, for either of these two triangles, this is the base, this is the base, this is the height, this is the height, right? So it's going to be, for a triangle, IX equals 1/12 base times height cubed, 1/36 base times height cubed. For the rectangle, it's base height, so it's IX, so IX equals 1/12 base times height cubed. And for a circle, I'm not sure that I remember this one off the top of my head, but I believe it's pi r to the 4th over 4. Okay, so if we plug these things into the calculator, you know, obviously the radius, the only kind of remotely tricky thing about this is that the radius here is 12.5. I think I made a mistake on that in my first, I forgot to divide by 2 the first time I did a key. So, you know, we all do that, right? So if we plug in the numbers, you know, we already know what all these things are when they plug in. So for this one, it's 50 times 110 cubed divided by 36. So the IX there, it should be obviously that this is going to be the strongest one because it's the most vertical, right? We're trying to bend it around this axis right here. Okay, so the more vertical you are, the larger your ability to resist that bending is. Okay, and then for this one, we're going to do the base, which is 50, and the height here is 65 cubed, and then divide by 36. And we get 381,424. And then for this rectangle, it's base, which is 50 times the height, 45 cubed, and we'll divide by 12. And we get 379,688. I found these two results to be interesting, that these two were similarly difficult to bend. And it shows you the power of being more vertical, right? Because this is just a little bit more vertical. This is a 65. This one's 45. But this one has way more area, right? And so it's just like going a little bit, you know, it's like 1/3 more taller, and yet way more, almost the same difficulty to bend with, you know, almost, I mean, I guess we could compare the areas, right? You know, similar total amount of area, right? So it says something about how you should use your material when you get to design. And then for the circle, we're going to plug 12.5 in there, and we're going to get 19,175. Okay, and so if we add all those up, we're going to get 2,590,548. Okay, so your IX around the centroid, which is usually written like this, I guess, you know, everybody does it a little bit differently. So it's going to be the summation of the local bending moments of inertia, plus, you know, you got to deal with this, what do they call that? The parallel axis theorem. The fact that these things are not being bent around their local centroidal axis. Okay, so that's going to be 1,853,356. Oh, sorry, I never gave units to this, did I? Millimeters to the fourth. Millimeters to the fourth. Okay, millimeters to the fourth plus, right, this huge number, 2,590,548 millimeters to the fourth. Okay, so the IXX prime bar equals, well, let's ease up on those sig figs, and let's go back to 5. And it looks like, with that last 0 being significant, right? Millimeters to the fourth. Okay, so that's a rather massive number. But we're only going to report 3 anyway. So we're going to go down here, and I'm going to say, you know, 4.44 times 10 to the, because I only want 3 sig figs for my reporting, 4.44 times 10 to the 6th millimeters to the fourth. Okay, totally annoying thing that we have to, totally annoying value. Okay, so let's go to the last one. You know, I told you guys there was what did I say? I said I think I was going to roll a dice, and there was a 1/3 chance that we were going to get a frame, a 1/3 chance we were going to get a truss with joints, and 1/3 chance we get a truss with sections. And I rolled a 2, and 1 or 2 was going to be a frame, so we got a frame. Now, how do we know this is a frame? Well, right off the bat, we see that this is not, well, so DF is a 2-force member, right? Because it's got a pin and it's got a pin, right? But CDE, it's got 2 pins, and then it's got another weight that's not acting at the pin. So that's not a 2-force member. ACFB or AB, right? These are not pins, and then it's got interior things. Okay, so this is just, you know, it's not going to work. So we can't just work from the joints. And I haven't graded it yet, obviously, because I'm creating the video key. But I'm guessing that a lot of people probably tried to treat it like a truss. And I really don't know how I'm going to grade that. I guess it depends on whether or not there was some clear thinking inside of all of that, right? So, you know, because what we're always looking for, what I'm always looking for is thinking. You know, how clear was your thinking? You may have made a mistake. That certainly happens. But how did you manage, once you got there? So here's C, here's F, and here's B, right? Now, who created these particular naming conventions? I just don't know, right? So anyway, so I'm just gonna split this thing apart. It's a frame, right? This is what we have to do. So here's point C, here's point D, and here's point E. Okay, and I'm actually going to cut it right here because I don't care about that weight, right? So I'm going to go ahead and put that 2,000 pounds going down right here. And then there's going to be a DF in here somewhere, and maybe I'm going to make it like this. Unfortunately, kind of hard to line that up the way we'd like to do it, but, such is life, right? So here's DF. So here's point D. Here's point F. All right. Now, I don't usually do this, but I think I'm going to do it now. I think I'm going to kind of start thinking for myself about which way I think these forces are going to go. So I know E is down 2,000 pounds. Okay, and I think it's pretty clear that, hopefully it should be clear to you that member DF is going to be in compression, right? So basically, it's going to be being pushed on this way and this way. Okay, so that's compression. So this is going to be DF. It's going to be DF, right? Obviously you could assume another direction if you wanted to, but that's the direction I'm assuming. And we know it's going to be along its axis because it's a two-force member. So this is going to be DF, and it's going to have to go in the opposite direction, right? DF, DF. Okay, and then we've got joint C. Now, if I look at member CDE, DF, I'm assuming is going to go to the right. So I'm going to go ahead and assume that C is going to be being held and being pulled this way by by this force over here. So we're going to call that C in the X. Okay. I don't know which way C in the Y is going to go. Well, I do actually know which way C in the Y is going to go. And that has to do with the fact that every time you have a beam like this, if you've got a downward force here and an upward force here, in order for the moments to balance, you need this force to be down, okay? And if you think about that, try to imagine you put a pin right here, and you imagine this thing's causing it to go that way. This one has no effect on the moment, so this one's going to have to go the other way, okay? And of course, it doesn't matter if you assumed this incorrectly, but notice I've got the 2,000 going down here, and I've got DF sine of that angle going up here, right? So this CY, I'm going to go ahead and put down. If you put the wrong way here, it would have been fine. Okay, so here's CY, and over here, I'm going to put CY going the opposite direction. As long as you have these two CYs going the opposite direction, it'll be fine. Okay, and the real problem here, of course, is A and B, right? These are really problematic. Notice that these are, fixed supports. Okay, so A has, and I don't know which signs any of these are going to go, but A has an upward force, AY. It's got a lateral force, AX. And then it's got a moment, which I'm just going to go ahead and draw counterclockwise, MA, I guess, MA, right? And then at B, I kind of got the same things. I got BY, I got BX, and then I got a moment going counterclockwise, okay? And that's how we set this thing up. Now, once we've done that, hopefully, just a really quick glance tells you, a few things. First of all, this member has how many unknowns? Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns. Okay, so member AB is not something we want to get involved in. And notice the question that we're looking for here is we just want to know CX and CY. Okay, so we don't want to get involved in that if we can avoid it. Okay, remember DF, it's got two unknowns, or it's really got one unknown, DF, right? So one unknown, but it's kind of trivial. I already assumed that, df is going axially and it's going into each other, so it's like not very helpful. So let's go for, remember, CDE, and I wish I could kind of grab it and move it. Maybe I can, in fact. No, I can't. Okay, but let's just look at CDE, right? And I could just say, okay, if I was being, mindless, I could just go sum of the forces in the x. Oh, we don't want black there. Let's go with sum of the forces in the x equals 0. I could say the sum of the forces in the y equals 0. And I could say the sum of the moments around some point equals 0. Probably C. Right, that's usually going to be the easiest spot. Okay, so if I do the sum of forces in the x, I've got two unknowns, right? Because I've got Cx and I've got the x component of df. Okay, if I do the sum of the forces in the y, I've got two unknowns, right? I've got df in the y direction and cy, so maybe we don't do that yet. But if I do the sum of the moments around c, I've only got one unknown, right? And that's going to be the x component of df, right? So basically I'm going to take df, and I'm going to break it into its components. Here's one component, and here's another component. All right, so if we zoom in, so this is going to be df sine of that angle. This is going to be of this angle right here, and this is going to be df cosine of that angle. Okay. Now we can also notice that this is a 3, 4, 5 triangle. So this is a 3, this is a 4, so this is a 5. Okay. So the other way to do this would, or equals df times, the vertical is going to be 3/5. All right, 3/5. And this one's going to be equals df times 4/5. So I'm going to use the similar triangles just because it makes it easier for me. If you want to find that angle, sine of theta, you plug it in the calculator, you're going to get 0.6. So whatever you want to do. But I'm going to use 3/5 and 4/5. So for the sum of the moments, let's see if I can keep that in view while we create this equation. Okay, so we're going to need to go, let's see, so we're doing it around point C. Oh, notice that there's 3 unknowns on this. So we should be able to solve for all of this in one equation. Okay, so that distance is 8 feet, and this is another 4 feet, right? So that df, so the vertical component of that, df times 3/5, df times 3/5. Okay, now it's got a moment arm of 8 feet, and it's causing things to spin. It looks like they're going that way, which is counterclockwise, so it's going to get a positive sign. And then we're going to subtract that, and then we get that 2,000 pounds, which is a moment arm of 12 feet, and it's causing things to spin that way. So we'll go ahead and call that negative. Okay, notice df in the x direction is going right through the middle of C. So it has no moment arm. And cx and cy also both goes through C. So this is the end of our equation. So we go equals 0, and we'll solve for df. Okay, and I think df is something nice and pretty. Oh yeah, 5,000 pounds. Or 5 kips if you prefer. Okay, so there you go. Sweet. Okay, so now we're going to go back over here. We can do, let's see, in the x direction, we've got 2 unknowns. But I think, well, but we now only have 1 unknown, right? So we've got cx, negative cx, plus df times 4/5 equals 0. Okay, so we'll go negative cx plus 5,000 pounds times 4/5 equals 0. And so cx equals 4,000 pounds. Okay, and then we're going to do the verticals. Okay, and so let's see here. We've got negative cy plus df times 3/5 minus 2,000 pounds. Those are all of our forces, equals 0. And so we just need to plug in. So negative cy plus df is 5,000 pounds times 3/5 minus 2,000 pounds equals 0. Okay, let's zoom in so we can go ahead and solve that. It looks like we're going to get 1,000. So cy equals 1,000 pounds. Okay, I know I did that algebra fairly quickly. Okay, so then down here in our answers, we only wanted cx and cy. And all I was looking for here was the magnitudes. So cx is, if we want 3 sig figs, 4.00 K. Cy is 1.00 kips. Okay, Cool. So that's it. Just under an hour. All right. I hope y'all are having a good one. You should really try this second one with lateral boxes. Some of you are going to have done it that way. So that's going to... Anyway, hope y'all are doing well. Take care. Goodbye.